from the first talk of the day, right? This.
Right.
And everybody that will wear this shirt during this talk will get 2 extra minutes. Okay. So our first speaker is Roseanne Cheng. You have 20 minutes and 5 minutes for discussion. This is for all talks during this session with lunch. So
let me first load up. Hopefully that doesn't contribute to the talk time. Windows. Okay. Full screen. Where's full? Oh, Control L. Oh, God. Okay. Boker Tov. Today, I'd like to generally talk about simulations of tidal disruption, and then our current work done with collaborators Hotika Shiakawa, Julian Krolik, Tzvi Paran, Gilad Svirsky, and Scott Noble. Let's look at the classic picture. A star orbiting a black hole will come in and reach a distance known as the tidal radius and disrupt. If this star is on a parabolic orbit, then some of the debris is ejected out of the system, while the rest returns to the black hole around the tidal radius. The debris that first returns will have a semi-major axis A-min, which is proportional to the mass ratio between the black hole and the star. And it will return on a timescale tau, which is the orbital period of the semi-major axis of this most bound debris. In the traditional model, this disk will quickly form and have the geometry of roughly the tidal radius. This means that when it returns, debris will quickly circularize and have an accretion time scale which is much smaller than the period of first return, tau.
I discussed about this yesterday.
Yeah.
But still you discussed about this 30 years ago.
Sure.
And correct with the e to the minus 5 thirds
We-
that got wrong.
You're telling my story. We got it.
You got it, okay.
Okay, in fact, oh, well, right, okay. So good question to ask. Once we've assumed these things about quick circularization, what is the return rate of debris when it first returns? If we assume that these are ballistic debris that returns ballistically, and if we know what the distribution of orbital energy of the debris is, and if we know Kepler's third law, we can find this rate. If we know, so given the distribution of mass and energy, if we find that it's flat, like Evans and Kachanik did, and if we use the chain rule properly, as Stirl-Finney did, we find that the fall off is t to negative 5/3 for the return rate. If we jump and say what the luminosity is, if it's equal to this return rate, we find that it should be proportional to t to negative 5/3. Okay, so what we have is a paradigm that the accretion flare for a TDE should fall off as t to negative 5/3. We should ask some hard questions, I guess. Where does this come from? Well, as I said earlier, it assumes quick formation at around RT. And we say that the accretion rate is equal to the return rate, then it's proportional to t negative 5/3. If we assume that this is a radiatively efficient disk, then we have that the luminosity is proportional to t to negative 5/3. But, Mushune, this means that for 10 to the 7 solar mass black holes, this should be highly super Eddington, that the peak should be highly super Eddington, which conflicts with assuming efficient radiation. So, generally, or let me, I should say, so can a black hole accrete in a super Eddington way? This is open for discussion. There's a debate in simulations between Yanfei Zhang and Oleg Sadovsky. So this is an open question. It's another question. Where does the light come from? And at what wavelength? We don't really know. And how do jets form from TDEs? So how do we address these big problems? We answer simpler problems. So one question to ask is, what is the geometry of these disks? Arguments for, if we consider loss cone and rates arguments, they say that tidally disrupted stars are likely to be on marginally bound orbits. So in recent simulations by Guilachan et al. And Shiokawa et al., from disruption to the disk formation, a star was modeled on a parabolic orbit and disrupted by a black hole of roughly 10 to 3 solar masses. The initial orbit was at E equals 1, so eccentricity of 1. Also, the semi-major axis of the bound debris is roughly 5 times the tidal radius. These are geometrically different from simulations with bound orbits. There have been recent simulations done by Bonneray et al. And Hayasaki et al. With a mass ratio of about 10 to the 6, eccentricity less than 1, and the semi-major axis of all of the debris is roughly 1 to 5 or 1 to 10 times the tidal radius.
Roseanne, make a brief comment here. Our paper, the 2014 paper, there's both the 10 to 3 and a 10 to 6.
Do you show the simulation to accretion, though?
We do not do circularization, but there's
Right.
simulation of the 10 to 6 disruption
Right.
in that paper.
Right. You do the 10 to 3, you show the disk formation.
Correct.
Right. Okay. So for these bound orbit simulations, the tidal streams are close to the initial orbit. So some already have semi-major axis on the order of RT. Also for these simulations, the stream intersection angle is much larger than those for parabolic orbits. So this means that circularization is just easier to do. So these are geometrically different simulations. So for the remainder of this talk, I will focus on the accretion problem for disruptions on parabolic orbits. In the classical picture, debris will, when it first returns, it'll focus at periastron, producing shocks, known as the nozzle shock, and also shocks will occur with relativistic precession at the tidal radius. However, Kachanich showed semi-analytically that this nozzle shock is inefficient. With 3D Newtonian hydrodynamic simulations, Guilachan et al. Showed that it's also inefficient. And then more recently, in Shiokawa et al., the shocks at periastron, as well as shocks when the stream intersects, are not efficient enough with 3D GR hydrodynamic simulations. And so, as it stands, the shock at periastron are not efficient enough to circularize material, and we have that the accretion timescale is not smaller than the period of first return for the debris. Okay, well, hopefully I've shown and argued for the thought that detailed calculations of the accretion process are necessary. This is a very messy problem. It involves hydrodynamics, gravity, magnetic fields, and radiative transfer. I stress that the choice of initial conditions is very important, particularly for the initial orbit, but also stellar structure is important. So even with hydrodynamics and gravity, this is very, very computationally expensive, and this expense increases with mass ratio. So most previous work on parabolic disruptions have a moderate black hole to star mass ratio. And over the years, we have been able to model a fraction of this fundamental timescale, the return time, from a fraction to about to over 10 times tau. So, and now we'll show how we cut down the expense in Shiokawa et al. So we modeled the disruption, we modeled the system from disruption by a non-spinning black hole, and then its evolution of the debris streams around the black hole. We did this first by modeling disruption in a local moving frame following the star, known as Fermi-normal coordinates. Then we take the result of that simulation as initial conditions for evolution in the black hole domain. So here's a schematic of the results of our simulation, showing shock formation and angular momentum redistribution. Debris first returns to the black hole. Then as debris streams focus at periastin, there is the nozzle shock that forms. And after the stream wraps around the black hole, it'll intersect with the incoming stream and hit itself. And when this happens, shocks also form there. And in this process, some debris is deflected into the black hole, and that's roughly 30% of the bound mass. We have this disk that forms roughly on the scale of A-min, the semi-major axis of the most bound debris. Later in time, the geometry of the disk changes as it continues to hit itself. We see that in this process, the angular momentum distribution broadens. So, does the debris circularize? Well, not really. So, just to give you an idea, this is our initial condition, the distribution of angular momentum versus energy from the local calculation. Its corresponding distribution and eccentricity is here, where we start the global simulation at 0.6 tau, and it's in the black line. And then we see as it evolves in tau that the eccentricity decreases, but the median is still at a 0.4. So we are not getting it to be E equals 0, even at the end of our simulation. So now let's talk about accretion rates. Well, we like to actually say mass accumulation rate instead of accretion rate. So you don't know how things supereditingly accrete on the black hole very well. So we show this in two ways from our simulation. So this is a mass accumulation rate versus tau. We first show the actual rate of debris as it passes through our inner boundary condition at 30 m. Here we see this curve comes from the 30% of the bound mass that enters our inner boundary condition. At the end of the simulation at 12 tau. Then later we extrapolate with what remains in our simulation, and we extrapolate what the accumulation rate is from analytic theory, where we assume that angular momentum transport comes from magneto-rotational instabilities, and we choose two alpha parameters. And note that the fall off in this rate depends on details of magnetohydrodynamics. So these are rough estimates. So we take these curves and compare them with the ballistic return rate. And we see first that the peak is 10 times less. We also see that the peak is delayed and is flatter. Instead of about a 1 to 2, the peak is around 3 to 8. Your boundary condition, right. 30 m, 30 RG. Okay, so to summarize these recent results, we find that the characteristic length scale for a disk to form is at A-min, which is much greater than the tidal radius. We find that in addition to the shock of the nozzle, there are also outer shocks when the debris stream intersects itself, and we find that these outer shocks are due to relativistic effects. We find that 30% of the bound mass is deflected into the hole by hitting when the stream hit itself. We find that the remaining mass takes much longer to accumulate onto the black hole. We find that the peak is 10% less than the classical expectation. So we expect significant departures from the classical expectation for the light curve, and more on that, see Gilad Ziersky's talk.
Gilad will talk about the fraction of bound mass deflected into the hole for the 10 to 6 aspect ratio case, because presumably that number is under simulation.
This is from our simulation with the roughly 10 to the 3 solar mass black hole. I'm not sure what Gilad's going to talk about, but I know that he's going to talk about the aftershocks.
When you say deflected into the hole, you mean deflected into the 30 RGs, right?
Right. A deflected, the accumulation is calculated at the inner boundary condition at 30 RG. All right, so that's a summary of our recent work. But here we're currently working on a new method to model the tidal disruption of a star and its accretion flow. We're using a method known as the multi-patch method, where basically we run multiple simulations at once with different patches. Each patch has a different computational domain size and can have different physics and different time steps. The communication infrastructure was written by Hotaka Shiakawa. So we're going to use this big tool to model tidal disruption simulations, particularly with the self-gravity of the star in the disruption phase. This tool will be used to treat the problem with magnetic fields from disruption to the accretion flow, and also crank up the mass ratio. Let me show you a quick example, just a test problem to show the multi-patch method. So here we have 2 patches, Cartesian Minkowski space. The local patch has a higher resolution than the global patch. Here we are going to show a gas blob moving at a velocity in the x direction. On the top, we will show that the patch moves with the gas, and at the bottom, we're going to have just the patch being stationary. So we'll see that in the top part, the patch follows the star, whereas at the bottom, we're showing how the interpolation between the high resolution local patch moves with the global patch, or interpolates onto the global patch. So, okay, and so, where am I now? Right, okay, so this is just a teaser. So we were already working on the actual simulation of disruption, but we'll just show you the star warping. But this gives you an idea of our domain, which we have. So here's the local patch, that's the global patch, and here's the star being tidally warped before passing periastron. Okay. Tura.
The B is still not circular, right? That you identify significant eccentricity. But I have my picture is that this is a debris, which is like a continuous structure in one plane. So why does this circularization not take place? The debris with different eccentricities are constantly colliding.
So this is the eccentricity of all of the debris in the domain at the beginning of our simulation, right after the local simulation calculates disruption. And so all of this is highly eccentric. It's at 0.8, at the least at 0.8 to 1. And it's just over time, the shocks are not efficient enough. And so we have that it lowers in eccentricity, but it's still at 0.4.
Do you expect it to go down with time, or do you think it's saturated?
Well, so in the classical theory, this should happen at 1 tau. And so we've already modeled it at 10 tau.
And what is
Tau is the return period for the debris. So it takes the energy of the most bound debris, and it's the orbital timescale for that energy.
Is the debris still coming? Was it bound, or is it back?
This is from a parabolic disruption. So
The debris is coming all the time until.
right. Well, you say that. So let's just take the ballistic return rate, which is the actually calculates the return rate. So at about 1.2 or 2 tau, most of the debris should have already returned. So, yeah. Oh, right. I don't have it on this computer.
So I'd like to make a quick comment about the difference between the parabolic and the eccentric hydrodynamic simulations, which I think has some bearing on astrophysical circularization efficiency. So in your talk, you said that the reason that eccentric simulations see such efficient circularization is that the intersection angle is larger.
Right, and the debris eccentricity is already really low.
Exactly. So I think the bigger effect is that the self-intersection is forced to occur at a very small
Right, and at 90, almost 90 degrees for some cases.
Often at large angles, but I think the bigger effect is just GM overall, the available virial energy in the shocks, which can change by orders of magnitude. And the key thing here is that self-intersection radius is a fairly steep function of the pericenter in dimensionless gravitational units. So as Jane Dye showed in her research there, as you move to larger RP over RG ratios, the self-intersection radius moves very far out. So in the Shiokawa et al. Simulations, I believe the RP over RG was 100, whereas for realistic tidal disruptions around, say, 10 to the 7 solar mass black holes, it might be more like 10 or 15. And I think that would force a much closer self-intersection point, which would give much more efficient dissipation.
Right, but I mean, we won't really know unless we actually do the simulation.
Of course.
I should also say that the eccentricity for the debris for these parabolic orbits are much closer to 1 for increase in mass ratio. So we are actually showing debris, we're showing a simulation that has debris with a lower eccentricity.
Yeah, I like to disagree with saying that we won't know unless we do simulations. I mean, it's just basic dynamics around the black hole that dictates where it intersects with itself. So, I mean, it's pretty certain that you're going to have a high rate of dissipation close to the black hole when the relativistic effects are strong, so long as everything is coplanar. And I think that so far we haven't, in Kiyosaki, we'll talk about this later, but so far we're talking about in-plane precession, and that's just going to guarantee very high rates of dissipation.
Do you know what that rate is?
So it's a function of the RP over RT.
Well, do you know if it's efficient enough to lose all that orbital energy?
Yes, yes, it is.
We've done test cases looking at the self-intersection point as a function of RP over RT. And it's true that when RP over RT gets down to sort of tenants, then the asymptotic precession is very strong, and you do have intersections both there. But as you know, we said, that requires a fairly large mass ratio, and also you said it is a very steep function. So if you go down merely to a few tens of the fifth solar masses in one solar mass black hole, already the intersection points are way out. So you're not explaining. You might be able to explain a fraction of the event, but then you're left with all the others.
Right, right. And you have to understand that you dissipate some amount of energy at the collision point, but then eventually you do form a disk, and that disk is going to have to liberate energy and radiate out away. So that's going to give you an additional component, right? So you're going to have radiation from the collision point itself, but you'll inevitably form some sort of accretion structure that will have to liberate energy to accrete onto the black hole.
And the question is how long that takes.
Right. So we do need, we can make estimates, but we need details.
Right. So I just think the stream collision aspect,
Right.
I
But
think that part is actually reasonably predictable.
right, but we need to know things like where does the photons come out and what wavelength.
Right.
Right.
Although I basically agree with you on the scaling of the asymptotic precession. The fact that no one had even mentioned intersections that out near the apicenter until we did the simulation and found it. Suggests the frailty in prediction of
It's mentioned in words, but it is actually Mark Reed's paper, there's a few sentences on it where he talks about the perception of relativistic
Oh, yes,
effects.
that part. But the
He thought of everything.
we're not.
I have a very different question. So you said it depends on the stellar spectrum what you actually get. Is that only between the white dwarf and the main sequence star, or do you say actually that might be a route to distinguish them between various stellar types which might fall into that one?
Right. It all depends on, I guess, how much material gets pulled off. If you have some star with a denser core, the time for being stripped off is different. So.
There's only a finite number of stellar types in the world that do exist. So is that a route to actually mapping out the distribution of stars in the second together?
It's possible. There's actually, if you want to, I guess, look at some changes to the return rate, there's actually a paper by Guilachon et al. That shows this, the return rate changing for stellar structure. So, but it's possible. We just have mostly modeled polytropes.
I mean, so Morgan McLeod has Jamie here is actually going to be talking about white dwarf disruption with hydrogen envelopes. And so when they're polytropes, they're relatively simple, single structure type things. So when you have transition in stars, they density jumps and stuff. That can make it a little bit more complicated.
Open question.
There was another question.
So, why is it then that so many of the observations are showing at late times the delay curve is following something close to the classical prediction of the 2 to the minus 5/3? The debris is having such a hard time circularizing.
Well, it depends on how many points you have and what the bolometric corrections are. I'm not an observer, but this is what we have, what the physics shows.
Can you answer louder? Be louder.
Right. So we have an estimate of, well, I don't have it here, but we have a figure in the paper that shows the angular momentum distribution with the debris as a function of time, like we showed for the eccentricity. We can go over that, but right. So later, I guess. So you asked what the.
The question
I think-
is whether the mass that comes into your inner boundary,
Right.
does it have enough angular momentum to go in a circular orbit? Does it fall
I
radially
think,
onto the
I
black
think,
hole?
so I don't know the numbers. I think what we found that it would go into the hole, but it's possible that it can also hit other debris and come out, but I don't really know.
It goes in with a significant angular momentum. There are several reasons why we cut off a certain end. One was technicalities, hydro time step. But another was I think it was in that inner region, further progress inwards would be controlled by internal
The MHD,
stresses,
right.
which were not in the calculation. So wherever we can already would be curious anyway.
Right.
If you do, crude alpha modeling of the increasing rate of a thick disk, which are h-bar per half, the increasing rate inside you tends then into the thick. So once it gets in that close, then you get into the end state. It's how it works out in the usually not that big.
Right. So we cut off at R equals 30M, and we can't estimate anymore because we don't know the physics. If we use the ballistic rate to see what it was, I mean, it won't be much better than what we have right now. We can look at the plot.
I mean, Oleg, you're going to show this in your talk probably, if you go all the way down to how many times in the calculation. I was thinking about a simulation where I go under the horizon and degree, but this would be a completely different simulation, much closer to time.
Okay, this was a great start. Thank you
Thank
very
you.
much.